Welcome to the Harper Classroom series of instructional videos. I'm Dr. Harper. This video is on Stochastic Inventory Theory Part 2, Single Period EOQ with Excel. This is Part 2 of a 4-part series, and this single period EOQ is the economic order quantity for a single inventory period. So let's start with a stochastic demand, which follows a normal distribution with a mean mu and a variance sigma squared. And we have only a single inventory period. In other words, at the beginning of the period, we order Q, and that Q will last for one period at the end of the period. But during that inventory period, a couple of things can happen. The first, we can have a long order quantity, where demand is less than our lot size Q, or we've ordered too much. Now, if we've ordered too much, then at the end of the period, we'll have remaining inventory, and that would be costly. The second thing is a short order quantity, where our demand is greater than our lot size Q. We haven't ordered enough. So during this inventory period, we've run out of inventory when we have demand, and that's unmet demand, and that's costly. But unmet demand is referred to as stock out. So now let's define some terms. For the long order quantity, let's define long cost, C sub long, and that's the cost of remaining inventory. There's a lot of different costs that go into the cost of remaining inventory, such as salvage cost and disposal costs or recycling cost. Let's define the expected long cost, which will be the probability that we will have remaining inventory times the cost of that remaining inventory being long. Next is a short order quantity, where we don't order enough, or our demand is greater than our lot size. Let's define a short cost, which is the cost of stock out or unmet demand. And that cost is lost sales, lost opportunity, lost branding. We'll define an expected short cost, which is the probability of being short, times the cost of being short. Now we'll use these two definitions to derive the EOQ equation. The optimal lot size Q is when the expected short cost is equal to the expected long cost. I don't derive this relationship, but it's essentially a break-even concept. This is equivalent to this expression where I take the probability of D less than Q, and I just replace this with 1 minus the probability of D greater than Q, because now I have the same probability. I can solve for that probability and have this relationship. But notice the probability is the demand greater than Q, which is being short. But being short is having stock out, and the probability of that is the probability of stock out. Let's represent that with alpha as the probability of stock out, which is given by this relationship here, and that's called the stock out level. So the stock out level is the probability of stock out. Since a lot size Q, which satisfies this relationship, represents the optimal lot size, we will use the expression Q sub alpha, where alpha is the stock out level. Now from the standard normal distribution, we have the probability of Z, the standard normal random variable, greater than Z of alpha, the standard normal random variate, equals alpha. And this was given in part 1. Also from the standard normal distribution, from the transformation, we can transform the random variable D to the Z by subtracting the mean and divide by the standard deviation. This was also given in part 1. But now I have two equations that are the same except for the random variate. I can set the random variates equal, and I have this relationship solve for Q, and now I have my equation for my optimal Q. So this Q of alpha, since it optimizes the lot size and minimizes cost, we call it EOQ, and it's the mean plus Z of alpha times sigma, where this alpha is the stock out level, and it's given by this ratio of the long cost over the sum of the long and short cost. So let's look at the concept underlying this equation. Since our demand follows a normal distribution, in part 1, we saw how the random variable D follows a normal distribution with a mean mu, and D sub alpha is a random variate, a value of the random variable, where the probability in the tail is alpha. We also saw how we could transform the D to the standard normal distribution z with this transformation equation. And if we want to transform a z back to a d, we can just solve this for d, and we can transform it back. Notice how this expression and this expression are the same. And so the random variate d here is essentially the same as the q. And so the q is nothing more than the number of standard deviations above the mean of the normal distribution of the random variable. Another way to look at it, since alpha is the probability above that random variate, then 1 minus alpha is the probability below the random variate. Well, the probability below, or the percentage of the distribution below, is nothing more than a percentile. In other words, if alpha is 0.1, 10%, that means the probability below is 90%. So that's a 90th percentile. And so what the EOQ single period stochastic demand equation is doing is just finding a percentile of 1 minus alpha. So let's do some mechanics and solve a problem. The demand is normally distributed with a mean of 539, a variance of 67.24. The long cost is $3, the short cost is $27. And usually the short cost is greater than the long cost. The stockout level then would be 3 over 3 plus 27, which is 0.1, and the service level then would be 90%. The z value, which is approximately 1.282, we can get that from Excel using the normal standard inverse function of 0.9, which is the service level, and I'll do that in a minute in Excel. The equation, we bring down the mean of 539. Z then is approximately 1.282, and sigma, which is the square root of the variance of 67.24, doing the arithmetic, we get 644.087, which is approximately 645. Notice I rounded up. You could either round up or round down at this point. It's not that critical. I rounded up because the short cost usually is greater than the long cost. So if you want to round one way or the other, usually you round up so that you lower the probability of being short. Since I rounded up, my probability of stockout is a little bit less than 10%. So let's solve this with Excel. So I've typed in the headings and the equations, so let's type in the values. The mean is 539. The variance is 6724. The long cost is $3, and the short cost is $27, and that's going to equal an alpha of 3 divided by 3 plus 27, which would be 0.1. So now our z is going to be the normal standard inverse of 1 minus my alpha, which is my stockout level, and 1 minus alpha will be my service level, which is approximately 1.282. It's actually 1.281552. So now the EOQ is simply going to be the mean plus my z times the square root of my variance, which is 6724. And there's the equation. And if we move this up, we can see that our 644.0872 is what we got. And that's how you solve this in Excel. So that ends the video on Stochastic Inventory Theory Part 2, Single Period EOQ with Excel. I'm Dr. Harper. I hope this helps. Thanks for watching.